Good afternoon. Hello, everyone. All right. Hi. Hi, my name is Penny. I'm a librarian here at the library. And I just want to welcome you all here. What a great turnout. And just want to remind you all to turn off your phones, or at least turn them down. And I'm not going to take much of your time. I just wanted to give you all welcome. And we are super excited to be partnering today with the Boulder County Parks and Open Space. I wanted to make sure I said that right. And with that, I will pass the mic over to David, who will be doing our presentation today. Thank you.
Thank you, Betty. Well, thanks so much for coming on the first warm, sunny day in a while here. I almost didn't want to come inside myself, but I did. So I'm David Copeland, and I'm a volunteer naturalist with Boulder County Parks and Open Space. How many people have done a program with Boulder County Parks and Open Space in the past? Well, that's great. Well, we have all kinds of stuff going on. In addition to talks, we have a lot of hikes and outdoor programs at all our different open space programs or sites. And at the end, I'll show you how to find those programs and register for them. So today we're going to talk about Story in the Rocks, the spectacular geology of Boulder County. And okay, let's begin. So really what we're going to talk about is the geologic history of Boulder County. But what I want to focus on is interesting geologic features you can see in the parks. And looking at these things, you could ask, how did that happen? And to me, this enriches my appreciation and enjoyment of the outdoors when you can see things and say, oh, there's that thing, and I understand how that formed. Okay, so just a word about my background. Geology was my field of study in college and grad school. But I didn't actually work as a geologist. My first job was with a small company doing oil, gas, and mineral exploration using Landsat satellite data. And I ended up kind of veering off into the image processing side of things. And the first half of my career, I did image processing and machine vision. And then the second half, I did education. I led a small nonprofit, educational nonprofit, and then I taught high school science for 13 years, so done a lot of science and teaching, and now I'm so happy to be able to combine that being a volunteer naturalist. I'm pretty new to Colorado, but I've been trying to get up to speed on what's going on around here in terms of the geology. One of the great things about Boulder County is that, many great things, is that they have really fascinating geology here. So here's an outline of what we're going to talk about. Just going to go over a few key ideas from geology, probably things that way back you may have learned in school. And then we're going to kind of work through time here. First, how did Colorado form? Because Colorado wasn't here forever. Before Colorado, there was no continent here. And then we'll talk about sedimentary rocks in the foothills and plains, the rise of the modern Rockies, and finally the glacial geology of the area, which is quite interesting. So to kind of make this a little interactive and keep you on your toes, once in a while I'll show a picture with a question mark, and if you know where that picture was taken, raise your hand, you can tell us. And there's no penalty for wrong guesses, wrong answers. Okay, a few key ideas from geology. First thing is, we live in a really unique location on the continent. If you starting from where we are, you can go 1,000 miles east and you're just on plains. And you go 1,000 miles west, you're in mountains. And right here, the mountains just jump right out of the plains. And of course, every time we go outside, we can see that. And I'm just amazed every single time I go up close to that boundary, like on 36, how sharp it is. They're, just this gradual, quite flat, and then wham, these mountains just jump right out. So we live in a special place. And that line is the Continental Divide. Well, actually, what is not quite the Continental, that's the front of the mountains. But the Continental Divide of course, is right here. And we're actually also the easternmost point on the Continental Divide in North America. So that's another curious thing about Boulder County. So this is in recent years, this has been an interesting way that people have been portraying geologic time. Instead of like a linear sequence or like a layer cake kind of look, which is how geologists often think about it, this spiral, which kind of shows time going back, conveys the idea of deep time. So it's really impossible for us to grasp intuitively how old the Earth is or how old the universe is. It's just so much greater than our human time scale. But one interesting thing about this presentation is that it kind of illustrates that times that are closer to us, we know much more about. So like we know a lot about the last 65 million years. That's called the Cenozoic in geologic terms, the Cenozoic era, after the dinosaurs died out. And we know quite a bit about the period of the dinosaurs, which is the Mesozoic, middle life. And then this is older life here. But even all that time is only a little more than 10% of the age of the Earth. It just goes back and back and back and back. And we have very little evidence of what was going on way back then. So how do we know the Earth is so old? How do we know that a rock is any particular age? Well, it wasn't until 150 years ago, or a little over 100 years ago, that we really knew how old the Earth was, when this radiometric dating technique was developed. And not to go into too much detail, but the idea is that certain radioactive elements, like potassium-40, an isotope of potassium, decay to a daughter element, in this case argon-40, at a very predictable rate. And so if you take a rock sample and you have the right equipment, you can measure the ratio of the potassium-40 to argon-40 in the rock, and the argon can't get out because it's trapped in the crystal structure. And then you can calculate, well, that rock must have crystallized X number of years ago. And it's not, it's within a few percent kind of thing, but it's enough to get a very good idea. And before this technique was developed, I mean, in the 1800s, people started to get the idea that the Earth was much older than we thought, from things like clam shells in the Himalayas, like, the heck, But even then, after their best estimates were in the hundreds of millions of years, not the billions of years. So this kind of told us what's really going on. And you may remember about the rock cycle. This is kind of a complicated diagram, but we have igneous rocks, which form from molten rock, either underground, called magma, above ground, called lava. We have sedimentary rocks, which form by the weathering and transportation of other rocks, so usually deposited by wind or water. And metamorphic rocks, which are formed due to great heat and pressure. And they didn't actually melt, but they usually show wavy or banded patterns that indicate that they came close to melting, and the minerals resegregated and recrystallized. So we'll use those terms a little bit. Okay, so how Colorado formed. GA means billions of years. I'm using the geologic thing for that. Giga-annum. Billions of years. So 1.8 to 1.4 billion years ago, that's our first time period. Okay, here's our first question mark. Yes? Long speed, yes. So which is what Longmont, of course, is named for. And okay, here's another one now. Anybody recognize this place? No? Emerald Lake, no? Well, it's the Indian Peaks area. Indian Peaks, yeah. Lake Isabel. Did somebody say that?
Yeah.
Yeah.
Pleasant Valley.
Not sure about Pleasant, what that is, but. So I just wanted to show you some pictures of these big mountains. And interestingly enough, when the Louisiana Purchase was made, it was specified to be up to the Continental Divide. Nobody even knew where that was. And so Major Long came out in 1820 to figure out, like, well, what did we buy? And he, discovered that we bought Boulder County. Because the Continental Divide is the western boundary of Boulder County. Okay, so these big mountains, the mountain core, are made out of igneous and metamorphic rocks. And if we date these rocks, we keep coming up with the same numbers, which is about 1.7 to 1.8 billion years old. So something big happened 1.7 to 1.8 billion years ago. And this is called abandoned gneiss. And, we say in geology, never take gneiss for granted. So the way you can tell gneiss from granite is you'll see some evidence of banding or foliation, we call it. Right? So because this rock was metamorphosed at high temperature and pressure. So how did that happen? Here's another rock of about the same age, the Boulder County granodiorite. If you go up Boulder Canyon, you'll see this rock. In outcrop, it's often kind of brownish because that's what weathers do. But if you see a fresh cut, it's black and white. So this is also about the same age. So again, something big happened 1.7 billion years ago. And here's another one. This one's a little younger. I love this rock because of these oriented crystals. So the way this formed is it cooled at depth, slowly cooled at depth, and the crystals grew bigger and bigger and bigger. These are feldspar crystals. And then it was injected upward to a shallower depth where it cooled more quickly. So it cooled more quickly, the surrounding matrix here is made up of smaller crystals. So when you see this rock, you can recall that little sequence. This is called the silver plume granite. This is pink in its fresh cut. And I found this example is Brainerd Lake, but it's also, you can also see this up at Paul Ranch. You go up to the high part of Paul Ranch. So the big mountains, the mountain core is made up of gneisses and granites primarily, metamorphic and igneous rocks. And these are called the basement rocks. 1.8 to 1.4 billion years old, that's very old. Now, on the surface here in the plains, the rocks are much younger, and all the way out, to the Appalachian Mountains, there's younger sedimentary rocks. But underneath, there's still basement rocks, still very old igneous and metamorphic rocks. It's just that here in the mountains have been uplifted, and the sedimentary rocks have been eroded away, and so we see these ancient basement rocks on the surface. So how did these rocks in the state of Colorado form? Well, let's put this in context here. So 1.8 billion years ago, because there's nothing older than that. So there was nothing there before those rocks were formed, except ocean. So 1.8 billion years ago, where are we? Here's 2 billion years old. So we're like 40% of the way back to the origin of the Earth. So to understand what happened at that time, we have to do a little quick review about this idea of plate tectonics. And when I was in high school, it was around 1970, this was like a new idea, just becoming accepted. But it totally revolutionized geology because it provided an explanation for lots of things that previously we could only just observe and describe, and now we had an explanation. So according to this explanation of plate tectonics, and we have very good evidence for this, the Earth's surface is divided into a series of rigid plates. Each plate may have ocean crust and or continental crust. So here, this is continental crust here, and ocean crust here. Continental crust, ocean crust. The actual boundary is a little offshore between continental and oceanic crust. The continental crust is made up of lighter rocks like gneisses and granites, and the oceanic crust is made up of denser rocks like basalt, mostly basalt. Now, the boundary between the plates can be one of three types. They can be spreading apart, which is called a divergent boundary. And this is like along the Mid-Atlantic Ridge here. And when they spread apart, lava or magma from down below comes up and oozes out to the surface and forms new crust. So that's what creates the Mid-Atlantic Ridge and the East Pacific Ridge and other oceanic ridges around the world. Not a kind of a violent process, it's kind of a quiet process. But where they come together, we get a lot of action. Okay, so where the plates converge is where we tend to get things like volcanoes and earthquakes. So for example here, this little bit of Juan de Fuca plate is going underneath the Pacific Northwest. That gives rise to the earthquakes up there and also the volcanoes of the Cascades. Same thing down here in the Andes Mountains with the Nazca plate going underneath South America, and that creates a lot of geologic action. So geologists have busily gone around the world to try to explain lots of things we see on the surface in terms of plate tectonics. So about 1.8 billion years ago, this is maybe what this part of the world looked like. This was proto-North America, and this is where Colorado was going to become Colorado. And there was a plate to the south that was moving north under Wyoming. The rocks in Wyoming are actually older. Some of the rocks are over 2 billion years older than Wyoming. So this existed first. And the crust this plate was moving northward, and it was creating a series of island arcs like Japan, and trenches where sediment was coming off of the continent. So we have all kinds of stuff coming off: sand, mud, limestone. We also have volcanic rocks we can find up in the mountains in certain places. And all this stuff is moving up and crunching up into proto-North America. And it just basically glommed on and made the continent bigger. This is called continental accretion. And over time, the continents have gradually gotten bigger and bigger by this process. At the beginning, or very early on in the Earth's history, there probably weren't any continents. It was just oceanic crust. But then this process of continental accretion has gradually built up the continents over time. So Colorado was accreted onto North America 1.8 billion years ago. See, you got a mouthful of geology right there in one sentence. So, yeah. Go ahead.
So, this addition of the crust in the Earth comes from magma that comes from the center of the Earth?
I'm glad you asked that question, because I can explain it with this slide right here.
You got to repeat the question, please.
So,
Repeat the question, please.
the question was, where does that magma come from? Where does the new rock come from during this process of accretion? So here, this is like a schematic of what happens when oceanic crust is pushed down under a continent. And as I mentioned, this could be, today, this could be Japan, right here with the island arc being formed, or many other places. This could be the Andes and the coast of South America. So because this oceanic crust is denser, and it when the two collide, this gets forced down into the mantle, the hot rock down below. It's not melted, but it's much hotter. But because this contains water and a different mineral composition, when this is forced down into the mantle, it melts. And little streams of magma come up and create volcanoes. Plus, it creates this trench where it's going down, like the Marianas Trench, the deepest point in the oceans. That's an example of subduction. This is called subduction. And that trench tends to fill up with sediments that are being eroded off the continent. But eventually all this stuff just gets crunched together, and all this stuff, the volcanic rocks, the sedimentary rocks, all get squeezed together like toothpaste in a vice. Right? These two continents are coming together, and this stuff gets pushed down and pushed up, and this is where the metamorphism comes from. So all these gneisses, these banded gneisses, started out as sand, mud, limestone, volcanic rocks. They were pushed in this vice between the continents and turned into the gneisses, and also here's the granites. These are the granites forming here. They cool below the surface, and that became Colorado. Does that answer the question?
Well, I was going to say, did it leave a hollow spot, but you explained no, because things are going in to take its place on the surface.
Right. Did it leave a hollow spot?
That's what I didn't realize.
Right. I actually asked the same question when I was a geology student. Doesn't that leave a hollow spot? Yeah. Okay. Let's see here. All right. We mentioned a little bit about this, but here's a nice drawing. So when rocks melt below the surface, we call that magma. And two things can happen. It could either cool, come up and make a chamber of magma, and then cool below the surface. If it cools slowly like that, then the crystals have time to grow larger. And then we get things like granites. There's a whole suite of different names for those rocks depending on the composition, but for our purposes, granite is good enough. Another one is granodiorite, like the Boulder County granodiorite. But they all kind of look like this. They differ just in their composition and in their color. But also, it could actually come up to the surface and come out. Then we call it lava, like what's happening in Hawaii right now. I really want to go see that, but I'm not going to. And then we get very fine-grained rocks because they cool quickly. So this is like basalt, for example. Okay, so summary. Continents grow by accretion during collision events. Colorado was created about 1.7 billion years ago during a continental collision. And about 300 million years later, there was another event. We don't know really what happened, but possibly another collision or some other tectonic event which created more granites. And there's actually another one about 1.1 billion years ago. So, you know, things happen. And it's hard to know exactly what that long ago, what was going on. The Pikes Peak rocks are about 1.1 billion years old. So that was another tectonic event.
Dave?
Yeah.
I don't know what's got it. I thought those places were always moving and subducting and grinding.
True.
So for me, all the time, it's still 1.7.
Why are there like intervals like
So
that?
long.
Great question. So why are there certain intervals? Why isn't it just always happening?
Oh, it's
So this is like the very big picture about plate tectonics, which is fascinating to me. But we have good evidence that there's a recurring pattern where the continents all come together to make one supercontinent. And like the last time, we call that Pangea. But then that's like what happens then is it's like you put the lid on the pot. The mantle heat can't escape as easily. And so heat builds up over time, and then that changes the way the mantle is flowing, and continents split apart. But then once they're split apart, there's eventually less force driving them. And they eventually kind of come back together. There's this repeating cycle, which happens to be about 300 million years.
So it's being driven from underneath
Yeah.
actions and the
Heat
pressure.
coming from the Earth's interior is driving the motion of the continent. Some people compare it to the continents to scum on the surface of a stew. And if that's the continents, what does that make us? Yeah. So now we're going to make a big jump in time because we have no rocks between 1.4 billion years old and 315 million years old in this area. There are rocks in other areas, of course, and even nearby, like in the Grand Canyon, for example, we have rocks that go back like 600 million years. But right here in Boulder County, the oldest rocks after the basement rocks are about 315 million years old. Why is that? Well, we don't know, because there's no record of what happened. But probably there were rocks here, and they were eroded away during subsequent mountain building and whatever went on over all those millions of years. So the story's going to jump forward to 315 million years ago. Let's take a literally a bird's eye view here of Boulder County. And there's a very interesting pattern that emerges here. All the rocks from the Flatirons east are sedimentary rocks. And all the rocks west of that are igneous and metamorphic rocks. Igneous and metamorphic rocks. So how do we explain that? You know, in science we always look for patterns and then try to explain it. Like that's a really dramatic pattern. So this figure comes from a really great book called the Geology of Boulder County. If you're interested in the Geology of Boulder County, I highly recommend it. Unfortunately, I think it's out of print, but you can still get it on Amazon Marketplace. And he goes into great detail, but for the lay person, about the geology of Boulder County, and also there's 25 field trips in here you can take around and look at different interesting things. And to me, this is a very helpful diagram in understanding the geology of Boulder County. We'll keep coming back to this, actually. So here's the basement rocks, the gneisses and granites, the ancient Precambrian rocks. And here are the sedimentary rocks on top of the basement rocks. Now normally sedimentary rocks are laid down horizontally, like a layer cake. And that's what we see over here. In fact, if we were to go out this way, all the way out to the Mississippi River and past, those rocks would be, you'd see basically the same rocks for one thing, and for another, they'd be pretty much horizontal. But when we come here to Boulder County and the Rockies, all of a sudden those rocks are tipped up and pushed up like this. And this is because this happened during the formation of the Rocky Mountains. And that's really fortunate for us because we can now see all these interesting rocks. And plus these provides very interesting terrain where we can have parks and we can do mountain biking and hiking and all kinds of good stuff. So we're really going to focus on this area here. Here's the Flatirons sticking up. And that's the first thing we're going to talk about. Now, in geology, because rocks are laid down one on top of the other, the oldest rocks are at the bottom. So, if you were to drive up, for example, Left Hand Canyon or Boulder Canyon, or any of the canyons here, you're basically driving back in time because the younger rocks, you would count the younger rocks first, and then older, 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 older. The oldest sedimentary rocks, the Fountain Formation and the Lyons Formation, and then you're into the Precambrian rocks. So I encourage you, while still driving safely, to keep your eyes open as you pass through the rock cuts. And then, and as a starter point, try to see where you get this transition from sedimentary to igneous and metamorphic rocks. That transition right here is called the Great Unconformity. I've always been fascinated by that term and by that thing. The Great Unconformity, because it's actually quite common throughout the world. Almost every place throughout the world, there's a gap between the Precambrian rocks, the really ancient basement rocks, and the overlying sedimentary rock. There's a gap in time. So unconformity means they don't conform to each other. Right? There's something missing. In this case, there's a whole lot missing. There's over 1 billion years missing. And if you take our geology hike out at Hall Ranch, you get to jump across the Great Unconformity. You get to jump across 1 billion years of time. That's part of the hike. No extra charge for that either.
You mean, is the unconformity a mixture of both granite and the other?
All it is one thing lying on top of the other, and there's a huge gap of missing time. That's all. There's no rocks that were deposited for over 1 billion years. So it's not like they're mixed together or anything. It's just there's a boundary. If one sedimentary rock lies on top of the other, and it was deposited right after that in time, we call that a conformable boundary. But if there's a gap in time, then that's an unconformity. And lots of times the unconformity, shows evidence of weathering and erosion, because this was exposed to the elements before the next thing was put on top of it.
So what is that stuff? What is it?
Great question. The best place I've seen this exposed is on Flagstaff Mountain, the road, Flagstaff Mountain Road, Flagstaff Road. If you drive up there, somebody told me it was there, and I drove back and forth until I found it safely. There's a spot, right, where you've got the mountain formation, which is big, which is sandstone with pebbles in it, red, very distinctive, and then right on top of it, right on top is, below that is granite. But if you walk over to the granite, it's so soft you can pull it out with your hand. It's been completely weathered, it's still in place, but the minerals have been all weathered to clay. And you could actually pull out a chunk of it because it was exposed to the surface for a long time before sedimentary rocks were put on top of it. Okay. So now let's put this into context here. 315 million years ago, the age of the dinosaurs is the Triassic, Jurassic, Cretaceous, which is together called the Mesozoic or Middle Life. But 315 million years ago is just before that. So it's around here, just before the age of the dinosaurs. And these are the oldest sedimentary rocks in Boulder County. Easy one. You're going to guess it. Flat irons, Boulder flat irons. Okay, anybody know where this is? Yeah, Hall Ranch and Lyons. But did you know that this is actually the same rock formation as the flat irons? Okay, this is the Fountain Formation, named for Fountain, Colorado. Usually geologic formations are named for a locale where they were first described by a geologist. So this was first described in Fountain, Colorado. And let's take a look at that rock. So we have this interesting concept in sedimentary rocks called sorting. If a rock is well sorted, then all the grains are about the same size. And if it's poorly sorted, then they differ a lot in size. What would you say? Is it well sorted or poorly sorted? It's poorly sorted. That's actually an important clue, because if sands and gravels are transported for a long distance, the action of the water sorts them out. Because water can only carry things at a certain size, or tends to carry things at a certain size, right? Let's say you have a stream running down like this St. Vrain Creek running past Hall Ranch. You know, if the size of the grains, the sand is smaller than a certain amount, depending on the current, it'll be washed down, and if it's larger, it'll settle down. So the stream sorts out things. If things are very poorly sorted, because this is a stream deposit, that means it was not transported very far. It was transported a very short distance. In fact, that kind of very poorly sorted sediment, which is sand and gravel, and also has other interesting features. It has chunks of granite in it. Some of the pieces are kind of sharp. They haven't been rounded by the action of water. Also, there's some soft minerals that have been preserved, like these feldspars. They don't last very long when they're being beat up by a stream. And so we know this was transported a very short distance at a high gradient. And so a modern environment that does that is an alluvial fan. Here's a picture of an alluvial fan. But to have an alluvial fan, you have to have mountains. And so based on the fact that there is a fountain formation there, which was an alluvial fan, which had to come out of a mountain, we infer there must have been mountains there at that time. But they weren't the Rockies. The Rockies only formed about 65 million years ago. So there must have been another mountain range before the Rockies, and we call that the ancestral Rockies. And so this thought process that we've just gone through, this is what geologists do. They're basically a form of detectives, right? You look at evidence, you think about, well, maybe this could have been this, could have been that, how could that have happened? What was the sequence of events? So that I've just told you, now we know why we believe there was a mountain range before the Rockies called the ancestral Rockies. Here's another interesting piece of evidence from the fountain formation at Hall Ranch. Does that suggest anything to you? What do you think how do you think that formed? Water, evaporation, mud, yes, all correct. These are mud cracks. And what tends to happen with mud cracks in geology is you know, just like in your backyard or your driveway, you get a layer of mud, it dries and cracks, but then another layer comes on top of that, like let's say a sandy layer, and fills in the cracks. And then later, after it's all become a rock, due to pressure and by the fluids migrating through the rock and cement it all together, the cracks tend to stand out as above, like ridges. So these are mud cracks. And so what does that tell you about, was this a deposit below water or above water? Above, yeah, below water or above water? Very much below? No. It's got to be right at the surface. It couldn't be like out in the ocean or at the bottom of the lake, right? It's got to be a terrestrial or land deposit. So this is what we think that the ancestral Rockies looked like maybe 310 million years ago. There's the ancestral Rocky Mountains, and there's all these alluvial fans flowing out, the streams. Here's some early plants that existed at that time. This picture is found in the Denver Museum of Nature and Science. In the outside the Hall of the Dinosaurs, there's a series of beautiful drawings or paintings like this called Ancient Denvers. And I'm going to show you a few of them, but they're like imaginings of what the landscape looked like at different times in the past. So here's what the landscape may have looked like. And they, the person that drew these put together the available evidence and came up with some reasonable guesses. So here's where we think the ancestral Rockies existed based on evidence, because we see similar deposits over on this side too, similar to the Fountain Formation. So why did that happen? Well, this was about 300 million years ago, and this is when the continents were coming together to make Pangea, which means all Earth. And possibly, now we're in the range of kind of speculation, but possibly the forces that were transmitted through the continent due to this collision resulted in the rise of the ancestral Rockies. At least it's about the same time, so. Here's another drawing about what may be going on there. Here's your basement rocks, metamorphic basement rocks. There's your granites intruded into the basement rock, into the gneisses. Ancestral Rockies and alluvial fans, making the, is now the Fountain Formation. Picture of granite pebbles eroded from the ancestral Rockies. One interesting thing about the Fountain Formation, like if you go out to Hall Ranch, you can walk through the Fountain Formation, and then at some point you hit the silver plume granite. And it's actually kind of hard to tell when you make that transition. And the reason is that the fountain is made out of pieces of the silver plume granite. And they don't look all that different. They're about the same color and so forth. Okay, what is this? Yes, CU. CU is a beautiful campus. And it's made out of a very famous rock called the Lion Sandstone. Here's Lucan and Brothers Stone Company in Lyons. This is actually the rock that went into my backyard to make my xeriscape backyard. Here, pieces of the Lion Sandstone. This machine is used to cut flagstones.
So flagstone is a part of sandstone?
Flagstone is just the use of it. Right? It's being used as a flag or something you walk on, essentially.
Flagstone is.
It could be other things, I suppose, but yeah. Flagstones are typically made out of sandstone. Yeah. This is a really beautiful sandstone. It's very hard. It's attractive, and it's used all over the country, and even in Europe, there are courtyards that are paved with the Lion Sandstone. Yeah. What do you think? Is it well sorted or poorly sorted? It is a very well sorted rock, so it can't be formed like the Fountain Formation. It's not an alluvial fan. Another interesting feature you see in the Lions is, so here are the actual bedding planes. In other words, this was horizontal at the time the rock was laid down. And the rock was laid down layer after layer like this. And yet, there's these lines that go at an angle, the bedding planes. And this is called cross bedding, because it goes across the beds. Here's the beds of the sandstone. And this is going across that. And what this is caused by is dunes. So if you think of a dune, right, there's like an angled slope on the dune. Like, who's been to Great Sand Dunes? Yeah, really cool spot. So you got this angled slope, and the wind blows over the dunes, and it keeps moving this way. So even though the sand is being deposited, let's say, at this level overall, the layers are going like this. Does that make sense? So that's what this is. You can also get this in deltas, like in lakes or the ocean where the delta is sloping down, right? And so there's an angle and it's being deposited on the leading edge. So this suggests that this is either deposited by wind, or maybe it's a delta, but it's certainly well sorted. Now here's an interesting question. Any idea how this could have, what this is and how this could have formed? But I heard it. Who said that? Raindrops. Yeah, these are raindrop impressions, and this is actually a flagstone in my backyard of the Lyons Formation. So if these are raindrop impressions, did it form underwater? I mean, under deep water, like a delta? No. This must have been formed above water. And so, again, this is just a very quick sketch, but if you put together all the evidence, we believe the Lyons was formed as dunes. They're dune formations, which are typically very well sorted. Like, yeah. The beach sands are also well sorted, but these are dunes.
Hey, Dave,
Yeah?
So, I have a place that had it out back too.
Yeah.
So what about the black moons?
Oh, yes, that's so interesting. It looks like branching, right? Black branching patterns. Yeah, they're very interesting. So those are formed by mineral solutions that are kind of creeping between the planes of the sandstone. And as they do, the crystals grow at the edge, kind of sort of like a snowflake in a sense. They call that a dendritic pattern for like branching, dendritic or branching pattern. Yeah, I don't have a picture of that, but that's quite striking when you see it. Yeah. Here's another interesting pattern in the Lyons Formation. This is actually a bench at CU. What could have made this, do you think?
Wind,
Wind, yeah.
waves.
Wind or waves, exactly. These are called ripple marks, and they can form either by wind or in shallow water. So by itself, this doesn't tell us whether it's shallow water or dunes, but it's a very interesting pattern. And I invite you to keep your eyes open when you're looking around CU or any place where the Lyons is outcropping or in your backyard. Do you see ripple marks? Do you see mud cracks? Do you see raindrop impressions? I mean, it tells you what geologists call the depositional environment. In other words, the environment it was deposited in. And you start to get clues about what was going on 300 million years ago. So here's the environment of deposition for the Lyons. Ancestral Rockies. Now maybe they've been worn down somewhat or were farther from the steep part. And there might be like streams that are carrying sand down from the mountains, and wind is blowing it around, making sand dunes, and that becomes the Lyons Formation. And here's perhaps an artist's conception from the ancient Denver's pictures. Notice the ripple marks there in the lower right. There's a stream carrying sand from the mountains and the sand dunes, like the Great Sand Dunes. So the Lyons is very hard. That's what makes it so valuable as a building material. And you'll often see a cap rock like this on top of a butte or a mesa. It's been eroded, the softer rocks above have been eroded away, and this is kind of protecting the softer rocks below. And so you'll often see this cap rock of Lyons, or sometimes the fountain too will do that, or depending on where you are. In the Grand Canyon, there are other rocks that serve this purpose. But anytime you see sedimentary rocks, you'll often see these resistant cap rocks. And one way to tell how hard or resistant to erosion a sedimentary rock is how steep the sides are. If it's very resistant to erosion, they tend to make vertical sides. And if it's less resistant, they make more sloping sides. So up in Lyons, this is Hall Ranch again, the fountain is not that resistant. It's chemically a little different than down around Boulder. Down around Boulder, it's very resistant to erosion. You get these very sharp flat irons standing out. Okay. This is kind of a tough one. It's like a wide-angle lens view of a beloved park. Any idea? Heil, yes, that is Heil. Heil Valley Ranch. We're on the south end looking north. And this is the valley itself. Okay, and here, these are the resistant ridges made by the Fountain and Lyons Formation. And then there are less resistant rocks down below. And then there's another resistant rock up here. Notice this nearly vertical here. So this is another resistant cap rock. And because this is east, and notice things are tilting this way, you can imagine the younger and younger rocks are piling up like this. So these rocks are much younger than these rocks. But this general pattern of a ridge here, a valley, and then another ridge, you can see that throughout the foothills in Boulder County. And these are called hogbacks. This is the Fountain Lyons hogback, and this one here is the Dakota hogback. So Ohio Valley Ranch is between two hogbacks. And then what do you think is to the west here? What kind of rock? Igneous and metamorphic, very good, right? Because now we've run out of sedimentary rocks and down to the basement rocks. Curiously enough, these actually aren't even as hard as the Fountain and Lyons. You'd think granite is like super hard or nice, but the Fountain is really quite. I mean, the Fountain and the Lyons, depending where you are, is quite resistant. Okay, so here's what I was talking about in terms of the hogback. Here's the resistant hogback made by the Fountain and Lyons, which around Boulder is the Flatirons. Then in between we have less resistant, younger rocks, the Lichens Formation, Morrison Formation, and then the Dakota hogback. And then we have more recent rocks. And this, we'll get to this more again, but this big fault here, you can see the rocks have been offset. That's from the rising of the Rocky Mountains. That's one of the many, many faults that caused the Rocky Mountains to rise up. So if you go to Ohio Valley Ranch and you walk around the Lichen Loop, of course that's all been burned now. How many people have been there since it burned? A good number of people. Looks a lot different, but it's still an interesting place, still a beautiful place. But one of the interesting things from a geology standpoint is the Lichen Formation has these rocks in it called stromatolites. These are fossils. And what they are is algal mats, the algae mats that build up these little mounds. And these have existed for a good part of Earth history. Here they are. This is an actual photo of stromatolites in Australia. They live in shallow ocean water. And this is a picture of the oldest known fossil, the oldest known evidence of life is stromatolites, 3.4 billion years old. So that's roughly 2/3 the age of the Earth. And these are stromatolite fossils, which don't look that different from the ones at Ohio Valley Ranch. You typically see these, when they break off, you see these kind of concentric patterns like this, or from the side you see mounds like this. So next time you're out there, keep your eye open. They're actually all over the place once you kind of get keyed into looking for them. And there's also an interpretive sign that will tell you about them so you can be reminded. So here's maybe what this part of Colorado looked like 250 million years ago. A shallow sea with stromatolites or algal mats growing. Morrison Formation It's very interesting rock. It's very widespread. There's dinosaur fossils are very commonly found in this throughout the West. Just south, named for Morrison, Colorado, just south of us. And of course, in Morrison, Colorado, there's the Dinosaur Ridge with the dinosaur tracks. That's the Morrison Formation. In this part of the world, in Boulder County, it's a softer rock, and so it tends to erode away. So the bottom of the valley at Heil is Morrison. And it looks kind of greenish. Let's see here. And so near the bottom where the stream is, you'll see the stream cutting through greenish rock, soft greenish rock. That's the Morrison Formation. And maybe this is what the world looked like. So now we're into the age of the dinosaurs, and maybe this is what Heil Valley Ranch looked like 150 million years ago. Okay, so now on to the Dakota. Dakota is in the Cretaceous period, the last part of the age of the dinosaurs. A lot of the famous dinosaurs that you're familiar with lived in the Cretaceous. They really should have called the movie Cretaceous Park. But that didn't sound as good as Jurassic Park, so they went with Jurassic Park. But the Cretaceous, the whole story of the Cretaceous in this part of the world is the story of the Cretaceous Seaway. So the ocean came in. The ocean came in and flooded the whole central part of the continent during the Cretaceous. During the early Cretaceous, we can see evidence of the ocean coming in and advancing over the land. In the middle Cretaceous, we see evidence that there's deep water here. And then at the end of the Cretaceous, we see evidence that the ocean is going out again. So the whole sedimentary sequence in the Cretaceous is about the Western Interior Seaway or the Cretaceous Seaway. Now, you may be wondering, how does the ocean get up to 5,000 feet above sea level? Anybody got an idea about that? Yes. We weren't that high yet. That's right. At this time, 100 million years ago or so, we were close to sea level. So that's another thing that needs to be explained, is how did we get from close to sea level to 5, 10, 14,000 feet above sea level? All right, that needs an explanation. But at this time, it was above sea level. But then you could also ask, well, it was about sea level. But you could also ask, well, what caused the ocean to advance and then retreat again? Well, what's that? Sorry, I couldn't hear you. Ice Age. Actually, partly, I think it's the reverse of an ice age, because there was no Antarctic ice sheet at this time. The world was a warmer place. The Antarctic ice sheet, if it was to melt now, would raise sea level about 200 feet. That's a lot. In fact, here's a fun fact for you. Do we have time for fun facts? We do. This boundary right here, there is a large concentration of Democratic voters right along that line. Why is that? Well, it's because that, when the Cretaceous Seaway came in, it left rock soils there, rocks that became soils that are very good for growing cotton. And later, cotton plantations brought in Africans who became African Americans who still live there and vote Democratic. So, I think geology isn't affecting the modern world. Think about that. Another factor that could have been having to do with the coming into the Western Seaway, Western Interior Seaway, is Pangea was breaking up at this time. And I mentioned the idea of a lid on a pot. Well, the well, the theory goes, I'm not sure really how good the evidence is for this, but it sounds interesting, that there was an increase worldwide in mid-ocean ridge activity that coincided with the breaking apart of Pangea. And so mid-ocean ridges are high because they're made out of warmer rock. And as the rock cools, it shrinks, and also they're like this mantle upwelling below it maybe. So if there was more mantle activity, then maybe the whole oceans were displaced by the swelling of the mid-ocean ridges that occurred at the time Pangea was breaking up. All right. So here's the Dakota Formation. Dakota Formation is like beach deposits that formed when the Cretaceous seaway was coming in. So that's the beginning of the Cretaceous seaway, beach deposits. Here's the Dakota hogback on Rabbit Mountain. You can see those resistant ridges. The Dakota is very hard. There it is, the Cap Rock at Rabbit Mountain. And if you go to Rabbit Mountain, you can see a lot of, it's a sandstone, so it's primarily quartz. You can see a lot of interesting features at Rabbit Mountain, like cross-bedding. In this case, it was probably beach deposits, we believe it was. And there's some pebbles. There's also, at Rabbit Mountain, you can see these interesting features. It's like scratches. Scratches in the rock. What could possibly scratch a rock like that? Glacier is a good possibility, but actually it's not what caused it in this case. Faulting. Faulting, okay? So there are all these faults along the Front Range here that have to do with the basement rocks being fractured and lifted up in big blocks to create the Rocky Mountains. And here, the Dakota Formation, which is pretty hard, has slipped against itself and made these scratches. They're called slickensides. Slickensides. And if you keep your eyes open just walking up the trail at Hall Ranch, they're all over the place. It's a lot, like a lot of things in nature, it's you look, where is that, where is that, where is that? And then finally you see one, and that's like, oh, they're all over the place. And that's how it is with a lot of these things we're talking about today. And I think it's kind of fun. I always get a kick out of it. Okay. So later Cretaceous rocks. So the sea has come in. It laid down the Dakota Formation as beach deposits, pretty well sorted sand deposits, very hard, making Dakota hogback. But now we get shallow water, then deeper water deposits as the ocean gets deeper and deeper. First we have the Niobrara limestone. This is a giant clam from Boulder County. It's just near Yoder Ranch. We're taking a hike out there in May if you want to go look at those giant clams in the Niobrara Formation. I'll give you the information at the end of the talk. And so limestones are shallow water, offshore, but shallow. Okay, then we have deep water deposits. The Pier Shale is deep water mud deposits that get consolidated and compacted to make shale, which is a sedimentary rock that comes from mud. And anybody have heard of bentonite? Well, everybody's nodding. Well, this is from the Pier Shale. Unfortunately, the Pier Shale underlies the bedrock for a lot of the Front Range. And when it weathers, it creates this mineral called bentonite that expands 5 times or more when it gets wet. And then it shrinks when it gets dry. And if that's next to your basement wall, it's bad news. So this has caused them millions of dollars worth of damage. Above that, this is what we call stratigraphic water, so the oldest is at the bottom. Above that, we have the Fox Hill sandstone. I'll show you some pictures of that, which is beach. Here's the water going back out again. Beach deposits of the Cretaceous seaway going back out again. And then the Laramie Formation, which is coastal plain deposits, which contain coal. These are coal seams here in the Laramie Formation. And this is what created the coal deposits in Marshall, Lafayette, Superior, yeah. So, again, it's all about the Cretaceous Seaway. And what this diagram is meant to show, maybe more interested people with geologists, but unlike most formations, most times sedimentary rocks are like older, medium, younger. But in this case, because the ocean was going out, at any given time, this was deep water, this was shallow water, this was on land. At a later time, this was deep water, shallow water, land. And so it's kind of an interesting pattern. Yeah?
What is Myers and
Mire is, like a swamp where things are decaying and making coal. Yeah. Like you said, he was caught in the mire. It can mean like a puddle of mud too. Yeah.
Do you have a time frame with the ocean coming in here? How long is it? Do you know how long that took?
We do know how long that took. Let me get my cheat sheet here. I have a different way of keeping track of all this information here. This is what they call a stratigraphic column. This shows all the different rocks. So I'm looking to see when the Dakota started. That was about years. Well, I think it's like 150 to 65 million years. So it started coming in about 150 million years ago, and went out about 65 million years ago. And the Beer Shale is very, very thick compared to the other formations. There's lots, like thousands of feet of mud were laid down. Okay, so maybe this was what our area looked like 70 million years ago when the seaway was covering it. And then only a few million years later, the sea has gone out and we're in a jungle. So this is the formation where the coal deposits are made. Near shore, lagoonal, swampy kind of deposits. Here's you want to see the Fox Hills Formation, the beach where the seaway was going out. This is at Sandstone Ranch, beautiful exposure of this. This was originally, we also do field trips out here. I think maybe it's the city of Longmont does a field trip out here. This was originally mined for sandstone before the lions, but the lions was so much better in terms of being hard that this was abandoned after they started mining the lions. And here's the coal mines in southeastern Boulder County. Here's the city of Boulder. Here we have So coal mining, of course, was one of the big industries in this area. In fact, there's many places along the Front Range that have coal. This is the richest coal area in the Front Range, and it supplied the majority of the coal to the whole Front Range for decades. Okay, rise of the modern Rockies. We're going to only say a few things about this. But basically, there were, for reasons that are not well understood, even now, I went online earlier this week and just see, is there anything recent about this? No. We just don't really know the details here. There's some theories. But we do know that there were large compressional forces. So the crust was being pushed together like this. Now what we know that is the angle of these faults. When the crust is being pushed together, you get the upthrust fault going on top like this. It's called a reverse fault. When the crust is being pulled apart, the angle would be like this. So we know that there was compression on a continental scale that was, and there's many, many faults. Basically, the basement rock fractured into big blocks, and the irregular blocks were pushed upward and also slid sideways. For example, Rabbit Mountain is about 3 miles out from the rest of the Dakota Outback. So it slid sideways along some of these faults. And the point of this slide is that before the modern Rockies, this is like 65 million years ago, something really big happened 65 million years ago. Anybody know what that is? Asteroid impact. Yes, that's what put an end to the dinosaurs. Did you know that? You did know that. You learned that in school? It's amazing. Okay. So when I was in school, that was just like, in fact, when I was in college, that was just like a radical new idea. But now there's plenty of evidence for that. So that was the end of the Cretaceous, the asteroid impact. And about the same time, the Rockies began to rise up, maybe a few million years before that. And before the modern Rockies, we had sedimentary layers like a layer cake, and then the basement rocks below, just like Kansas. And if this hadn't happened, we'd be living in basically Kansas today. So, for whatever reason, these compressional forces broke the basement rocks, forced up these big blocks. Now these things are way up in the air, and nature hates things sticking up in the air. And so it begins eroding them away, eroding them away, eroding them away. And now the basement rocks are exposed at the surface, but the sedimentary rocks down in the plains are still the ones on top. So that's the basic pattern we see. Now what caused that to happen? Not really sure. A theory that's been kicked around for decades, and I don't know how much evidence there is. There's some. But at about this time, this is North America. This is a plate that no longer exists, that used to be to our west, where the Pacific plate is now. And there was subduction going on. And at first, this was descending at typically a steep angle into the mantle. And the theory goes that it, for some reason, shifted to a shallow angle. See, the problem with the Rockies is that mountains almost always form near plate boundaries. And we're not near a plate boundary. We're way, the nearest plate boundary is 900 miles away. So that's a problem for plate tectonics. And so the idea is, well, maybe this plate that was subducted really extends underneath all the way out to our area, and that had contributed to the compressional forces that created the Rockies. But there are some other interesting things. Almost all Rocky mountain ranges have a mountain root, similar to an iceberg, right? Why does an iceberg float above the water, the above water part? Because 9/10 of it is below the water, and ice is lighter than water. And so the 9/10 that's below the water holds the 1/10 above the water to make it in balance. And mountain ranges are typically the same way, like the Himalayas, for example. There's lighter, lower density rock that goes way down, and that holds up the rock above. It's essentially floating on the mantle, just like an iceberg. But the Rockies don't have a root like that. That's a real puzzle. Another weird thing. There does appear to be like a dome of hot mantle below this area. And we can see a lot of evidence of that extra mantle heat. For example, the Yellowstone supervolcano, which I can't remember, 25 million years ago, when that went off. So, anyway, The conclusion is, not really sure. But one interesting thing that happened about the same time as the mountain building that created the Rockies was that a lot of mineral deposits were placed along the Rockies, and it's called the Colorado Mineral Belt. We're at the very northeast end of the Colorado Mineral Belt, goes all the way down to Durango, and there's gold, silver, tungsten, and other metals that are placed here. They're formed by hot solutions coming up from great depths that carry these minerals and place them in cracks in the rock. And this was exploiting a weakness in the crust. Probably the Rockies themselves formed partly due to this weakness also. And that weakness goes all the way back to when Colorado was glommed on to proto-North America 1.8 billion years ago, at the beginning of our presentation. So, you know, that ancient past is still having an effect today. Okay. Glacial geology. Thanks for your patience and attention. We're almost done. This is some of the most interesting and visible things we see around here. Anybody recognize this area? Yes, the diamond, and below it is called Chasm Lake. And if you're a hiker, this is like unbelievably beautiful destination on Long's Peak. And this is called a glacial cirque. And so during the last ice age, this was the head of a glacier. And glaciers literally eat their way back into the rock face. And they create this kind of amphitheater as they eat their way back into the rock, because I think I have a diagram on this. Let's see what the diagram is. Okay, so here's how a cirque forms. Here's the glacier, and as the ice is a very viscous fluid, It flows downhill, and as it flows away here, it exposes this, and frost breaks off pieces, so it keeps kind of eating backwards this way to make this like amphitheater of rock called a cirque. I don't know if I have the word cirque written anywhere. It's C-I-R-Q-U-E. And then it often like over excavates here, and you get later a lake. And then there is like a little hump here, and then a deposit at the end. The ice gets down to a certain elevation where it melts. It only gets down as far as it melts, as fast as it flows. That's what it's like, a conveyor belt. It's carrying down rock and debris, but as it gets further down, it melts faster and faster, and at some point, it's just an equilibrium where it's flowing in and melting at the same rate, and it just dumps all this stuff there over a period of time, and that's called a moraine. So you can see all those features here, let's look back here. So here's the cirque itself with the head wall. There's the glacial lake, which has a funny word, tarn, T-A-R-N. Then here's the little ridge past the tarn, the zone of abrasion. And this, in a minute, I'll show you a picture of glacial scratches that I took a picture of right here. There's the called glacial striations and polishing. So again, this is one of these things where it's like, the first time you see it and really recognize it, it's like, oh, that's glacial striations. And then you look around, it's like, it's all over the place. So I encourage you to look for these. You'll see the scratches are pointing down the valley, because that's where the ice was flowing. And it's also polished. And so the ice itself is not nearly as hard as the rock, of course, but the ice is carrying rocks along its base. It's kind of like sandpaper. Another picture of the polishing and striations. This is called a sheet back. They come in different sizes. This is a small thing, but you often get these sheet back shaped rocks where the ice has polished it and scraped it off, and the back side here, it plucks away the rocks as it as it flows over it. Another interesting thing is U-shaped valleys. I went to, when I was 15, my family moved to New Hampshire. I really liked New Hampshire. In fact, I think I moved to Colorado because I wanted to get back to having mountains again. And there's lots of U-shaped valleys in New Hampshire, but this is as good as anything you got in New Hampshire. This is the 4th of July trail. I just took this last summer. It's out past the old mining town of Eldora, which is down the hill from the Eldora ski area. The Eldora ski area is like over there somewhere, just over the next ridge. But if the valley is cut by a stream, it tends to be V-shaped. So if it's U-shaped like this, you know it was cut by a glacier. Okay, quick summary. 1.8 billion years ago, we had a continental collision. Colorado was glommed onto proto-North America. And that created all the igneous and metamorphic rocks that make up the high peaks. And then between 350 and 100 million years ago, we have the ancestral Rockies, which produced various sediments that we have today, like the Fountain and the Lions Formation. And then we have the advance of the Cretaceous Seaway. The Dakota Formation is the beach of the seaway coming in, and then we have deeper and deeper level sedimentary rocks with the Peter Shale, thousands of feet of that stuff. And then water goes out, and we have eventually the Fox Hills and Laramie with the coal deposits. And then we have the current Rocky Mountains, maybe 70 million years to present. There's been a couple of periods of uplift, but that's a whole other story. In glacial geology. Okay, here's some upcoming programs for Boulder Parks and Open Space, Boulder County Parks and Open Space. We have a foothills geology hike being led by Roger Myers, who's like the dean of volunteer geologists around here right now. He's my mentor. And then Fossils and Flowers hike on May 22nd, which is where we're going to see the giant clams. And there's usually several geology hikes each year, and you can go to discover.bouldercountyopen.space.org or Google that, and that's where you can sign up for, see what programs are available and sign up. Okay, thank you so much for your attention.